So in the last lesson, we looked at transformations of functions, and two functions in particular that we looked at. One was a linear function, which we call a function of degree 1, which develops straight lines, and a quadratic function, a function of degree 2, which develops either a U-shaped graph or an N-shaped graph. And what we looked at particularly was ways in which we can transform these graphs by horizontal movement, by vertical movement, and by narrowing. What I mean by narrowing is moving the graph closer to the y-axis. Okay, so just very quickly to review that, the linear function or a function of degree 1 are best used when you rearrange the linear equation into a form of y equals mx plus c. Now what does that mean? Say for example I had 3x plus 9y minus 12 equal to 0. Okay, if I wanted to use this in its best form, its most usable form, a form which actually reveals a lot of information about this function or about this particular line, what would I do? The answer is I would strive to get y on its own. Now let's do that. So in other words, we're going to eliminate 3x and minus 12 by taking 3x and adding 12, and we do that to both sides. So we get 9y is equal to minus 3x plus 12. And then in order to get y on its own, we simply divide both sides by 9. And that ends up giving me y is equal to minus 3 over 9x plus 12 over 9. Now they simplify. So y is equal to minus a third x plus 4. Now why is it that that particular format is the best format in terms of the function of a line? The answer is because it reveals two things about that particular line, and here it is. First of all, it reveals the slope of the line, and secondly, it reveals where it cuts the y-axis. So in other words, from that particular y equals mx plus c, I can sketch that function. So I could say, if you notice here, that the line would go through the point 4. So the line passes through the point 1, 2, 3, and 4. The line passes through the point plus 4 on the y-axis, which is here. Okay, and then the slope is rise over run. So in other words, we're going to drop down 1 unit and run out 3 units. 1, 2, 3 to here. So immediately I have a sketch of what that function of 3x plus 9y minus 12 is going to look like. So it's a very handy form of a linear equation for the 2 points of information that it gives me. Okay, and we've said that already. Changes to the value of m will change the slope. So therefore, the higher the value of m, the greater the slope. And what I mean by that is that if you have a line that runs this way, okay, say your line runs like this, and then you've got a second line that runs like this. Now here's what I know. If that's the slope of the first line and that's the slope of the second line, I can tell that the second slope is larger than the first slope for the very simple reason that the line is closer to the y-axis. See that? Or yeah, to the y-axis. And because it's closer to the y-axis, its slope is steeper. So you could ask yourself a question: which one of these mountains would be harder to climb? And the answer is obviously M2, because it's steeper. So if you were starting down here and you were going to try and climb this thing, and then starting down here and trying to climb this thing, you'd have a steeper slope to climb, making it a harder job, making it a greater slope, therefore it's closer to the y-axis. So these little things that help us as we move along. Now what other value can I change? Well, the other value I can change is the value of c. And what the c value change does is it simply moves that line vertically up and down the y-axis. It changes the point at which the line goes through the y-axis. Okay, quadratic functions. Now quadratic functions are best used when they're in this format: a times x minus h squared plus k. All right, we haven't really met this format yet, and we haven't seen quadratic equations written in this format. But in this lesson, and it's going to be a short enough lesson today, I'm simply going to show you how do I turn what I consider to be a normal looking quadratic equation into this form. Because there are three things here that this particular form will tell me: the a, the h, and the k. Okay, first of all, the a will tell me about the width of the particular U shape. The h will tell me the horizontal position, and the k will tell me the vertical position, because that's the final constant. So there are three things in here that we can work out if we're able to rearrange a quadratic function into this format. A being the constant which represents the width, constant multiplication, okay, or the coefficient as we call it. The value that's immediately attached to x inside this bracket represents the horizontal position of the function, and k represents the vertical. Now, the one thing I do want to say is this: if h represents the horizontal and k represents the vertical, well then there's something very important about the point hk, and there's also something very important about h on its own, and here it is. When you take the value of h and k together, you actually end up getting the turning point of that particular graph. And if you take h on its own, that would be the axis of what we call symmetry. Now, symmetry basically is a line that you put through something that allows you to fold it over on top of itself. Okay, now more about that later. That's just a little insight into where we're going to go in this lesson. So changes to a causes a change in the width, and again, the higher the value of a, the closer the arms of the graph will be to the y-axis. Or another way to say that, the higher the value of a, the narrower the graph. Any changes to h, because h represents the horizontal position, if you change the value of h, you move the graph horizontally. And finally, if you change the value of k, you will cause a move vertically. So, going forward, the best form of a linear function is y equals mx plus c. Rearrange if you have to. And then the best form of a quadratic function to use is the form which we call a times x minus h to be squared plus k. Now in there, see this x minus h to be squared? That can only come from a quadratic equation that has two perfect squares. Now, not all quadratic equations have two perfect squares, but we're able to mathematically rearrange terms in order to produce a quadratic that has two identical factors, and therefore will allow me to change its state into this one here. And that's what I want to do in the next one. So let's take an example of the completed square form, okay? And when we call it a completed square form, all it means is that present in the equation is an x minus h to be squared. So present in the completed square form is that x minus h to be squared, okay? Where we end up having a quadratic equation that can be broken into two identical factors. Now, how do we do that? As we said already, when we get that form, it reveals information about the shape, it reveals the vertex coordinates, and also reveals the axis of symmetry. Okay, so if a is greater than 0, we know this already. If you have a positive coefficient, well then obviously you're going to have a U-shaped graph. If you have a negative coefficient, then you're going to have an N-shaped graph. Okay, the combined values of h and k, as I said in the previous slide, will reveal the vertex. Now, the vertex is nothing more than the top or the bottom, depending on whether it's U-shaped or N-shaped. If it's N-shaped, it's the top point. If it's U-shaped, it's the bottom point, but that's the vertex we talk about. And finally, x equals h. If you take that value of h there and set it equal to x, then we end up getting the axis of symmetry. And again, the best way to do that is to take out that x minus h, set it equal to 0, and solve it. And when we do that, that is the axis of symmetry that falls out. Now, the best thing to show you here is an example. So f of x equals x squared minus 4x plus 7 as shown. At the moment, you can notice there are no factors of 7 that add to minus 4. So the way this is written is not really user friendly. So what I'm going to do is I'm going to remember this format here. Okay, and what I want to try and do with this quadratic equation is get it into that format. Now you'll notice that in this format there must be a quadratic equation that can be broken into two identical factors, and that's not the case here. So watch what I'm going to do. I'm going to keep the x squared and the minus 4x together. I'm going to keep the x terms together, and then I'm going to leave a gap. Then I'm going to put in the plus 7, and then I'm going to leave another gap, and then I'm going to put down equals 0. Okay, now why do I leave the gap? Why do I put a gap immediately after the 4x and immediately after the 7? And here's the reason. Because that is the way in which I transform a difficult quadratic into a readable quadratic. Watch what I'm going to do. Here's the answer. The term that immediately follows the minus 4x is the term that is half of minus 4 squared. Now, what's half of minus 4? Half of minus 4 is minus 2, and 2 squared is 4. So all of a sudden, I have added in a plus 4 that was not there before. Now, give a guess what the second space is. The second space is used to neutralize the plus 4 that I've just put in there. So because I've put in plus 4, I need to neutralize it. In order to keep the essence of the quadratic equation the same as the original, if I add in 4, I have to take 4 away. That then keeps the essence of the quadratic exactly the same. So this quadratic is still x squared minus 4x plus 7. By adding 4 and taking 4, you really are adding 0, okay? But what it does is it alters the shape of the quadratic in order to allow me to get it into this form here. Watch what happens. X squared minus 4x plus 4 immediately is factorizable. X squared is x by x, 4 is 2 by 2, and I want factors of 4 that add to minus 4. That's minus 2 and minus 2, which immediately contracts down into x minus 2 to be squared. And then the last two numbers, plus 7 minus 4, are plus 3 equals 0. Do you notice? The form that I now have is exactly the same as the form inside which we can read the vertex point and the axis of symmetry. Now, where's the vertex? Well, from this thing, the vertex of this function is, let's take out the x minus 2, let's set it equal to 0 and solve it. So the vertex is 2, 3, and the axis of symmetry is x equals 2. And they're the two things I get straight away, okay? So it's a very, very handy thing to do in order to take what is a normal looking quadratic equation, ones that we're very used to, and turn it into what we call the completed square form. And it's only practice that's going to get you to be able to do these things. That's why I'm only going to do that in this class. Okay, so you write down the coordinates. It says you write down the coordinates of the vertex and the equation of the axis of symmetry by putting them into the completed square form. So we've done this already. To write in the completed square form, you take half the coefficient of the x term and you square it. And then you rearrange the equation to its original value. So what did I do? I left a space after the minus 4x. There's the space I left there. And I also left a space at the end in order to neutralize whatever I'm going to put in after the minus 4x. I then take the minus 4, I half it, and then I square it. So half of minus 4, and I square it. And that comes out as plus 4, which goes in here. And because I've added in 4, I've got to neutralize the 4 by putting minus 4 at the end, which then gives me the term x minus 2 to be squared plus 3, which reveals straight away, look at it again, take out the x minus 2, set it equal to 0, and solve it. So there's the value of x in this function. Put it together with the value of y equals 3, and what do you get? The 0.23. Have a look at the graph. There it is. There's the vertex. And what's the axis of symmetry? The axis of symmetry is x equals 2. There's the axis of symmetry there. Meaning, if I go to the x-axis and put a line down through 2, I can fold the graph over on top of itself. All right, so it's a very, very handy thing to know and a very handy thing to be able to do. Okay, so you'll see in the box underneath that graph then, hence 2, 3 is the vertex and the axis of symmetry runs through x equals 2. So let's go to page 140, example 6.9, and see what it says here. Express the quadratic function y equals x squared plus 8x plus 7 in the completed square form and write down the coordinates of the vertex. Now, y equals x squared plus 8x plus 7. Here's what we do know. You can factorize this. There are factors of 7 to add to 8. So you could say, oh look, it's x plus 7 and it's x plus 1. However, in order to get it into the completed square form, the two factors have to be identical. And this quadratic as it stands doesn't deliver them. So let's take those factors away. And let's do the completed squared form exercise on this one. How do I do that? Y equals, keep the x terms together, then leave a space, then plus 7, then leave a space. Okay, now how do I fill the first space? Go to the coefficient of x, half of 8, and then square it. So a half of 8 is 4, and 4 squared is 16. So 16 goes in here, but because I have added in 16, I need to neutralize it with a minus 16. And now I'm beginning to get the form that I'm looking for. Okay, so let's do a little bit of tidy up on this. Take the new quadratic equation that's in there and write down its two factors. X squared is x by x, and by the way, once you develop this quadratic, it has to have two identical factors. Factors of 16 that add to 8 are 4 and 4. And then we have plus 7 minus 16 minus 9. So we end up getting x plus 4 to be squared minus 9. Now, what's the vertex? Well, take out first of all x plus 4, set it equal to 0, solve the equation. X equals minus 4. Take the last term, put that in there, y equals minus 9. So straight away, the vertex is minus 4, or the turning point is another way to explain that. Minus 4 minus 9, and there will be an axis of symmetry, and the axis of symmetry is the solution to the x part in the brackets. That's it. Okay, so could I sketch this? Of course I could. Let's take a look and see. The vertex is minus 4 minus 9. So we're back 4, down 9. So we're dealing with this part of the graph, just in case they ask you to solve or to draw, to sketch it. Yeah, back 4, down 9. So back 4, down 9. So that means that the vertex is down here. Okay, and because it has a coefficient that is positive, notice that there's a coefficient, it's 1 and it's positive, it's U-shaped. And it also says that the axis of symmetry goes through 4. So that means I'm going to graph like this. It's going to come down through that point, turn there, and away again. So I can sketch these things simply by rearranging a normal quadratic into what we call the completed square form. Okay, now let's take a look at this one. Worked example 611, page 141. Express the quadratic function y equals 3x squared minus 12x plus 10 in the completed square form. Now the reason I chose this is because if you notice in the previous two examples, let me just go back there, the quadratic equation started with x squared and this quadratic equation started with x squared. In fact, we can only use the completed square form on quadratics that begin with x squared. So the very first thing I have to do here is to take y equals 3x squared minus 12x plus 10 and take 3 out of everything. So y equals 3 times x squared minus 4x plus 10 over 3. And the reason why I have to do that is in order to get the quadratic equation where the x squared has a coefficient of 1, because that's what we're going to use to get the completed square form. So now let's get the completed square form. 3 times, let's just expand this a little. So what are we going to do? Keep the x's the same. Leave a space after the x, put in your 10 over 3, and then put in another space at the end. Okay, because you have to neutralize whatever you put in. Keep that in mind. So we end up again going to the x term. We take the minus 4. It's a half of minus 4 squared. Well, a half of minus 4 is minus 2, and minus 2 squared is plus 4. Now, because I've added plus 4 here, I have to take away 4 in that space to neutralize it. Okay, let me just take that off there. Okay, so now it's beginning to look a little bit more like the completed square form. Y equals 3 times. Now let's go in here and let's work this out. Do you notice that quadratic has 2 identical factors? X squared is x by x. Factors of 4 that add to minus 4 are minus 2 and minus 2. And then plus 10 over 3 minus 4. Now you can think of minus 4 as minus 12 over 3, because that is minus 4. So plus 10 over 3 minus 12 over 3 is minus 2 over 3. Okay, so what does that give me? Here's what it gives me. 3 times x minus 2 to be squared minus 2 when I allow the 3 back in again at the end. And what does that tell me? That tells me the width. I take out the x minus 2, I set it equal to 0 and I solve it. That gives me the axis of symmetry, and then that x value together with the final constant of minus 2, both of them together give me the vertex, which is 2 minus 2. So it's not really a difficult exercise, as long as you remember that when you're working out the completed square form, you must work with the completed square form only with quadratics that begin with x squared. So that's the first one. State the turning point of this function. Done. By considering the completed square form, solve the equation 3x squared minus 12x plus 10 equals 0, correct to 4 decimal places. And then it says sketch the function and write down the equation of the axis of symmetry of the function. Well, we've done that. The function, the vertex is 2 minus 2. The axis of symmetry, as we said already, because we're asked about the axis of symmetry, aren't we? Yep, the axis of symmetry, very simple. The axis of symmetry is just the solution of x, which means that I now have a graph whose vertex is 2 minus 2, and it is a positive coefficient, so again it's going to be U-shaped. So 2 minus 2, that's out 2 and down 2. So we're using here out 2, so oops, sorry, out 2, so out 1, 2, and down 2. So 1, 2, minus 1, minus 2. So where's the vertex? Out 2, down 2. So there's your vertex. Okay. What do I know? The axis of symmetry runs through that point. And then it's 3 times. So it's going to be quite a narrow graph, something like that. And that's the sketch. Okay. Now you don't even have to put the 1 in just to be safe that you have the graph, but it's only asked for a sketch, and once you're asked for a sketch of the function, that's perfectly fine. Okay, and that's that question. Okay. Last one before I give you some to do yourselves. Express the quadratic function y equals 7 minus 6x minus x squared in completed square form, and then state the vertex of this function and give the equation of the axis of symmetry. Now, what's the difficulty here? The difficulty here is that my x squared is negative. So at the end of the day, the completed square form can only be used on a quadratic equation that has a positive x squared term. Okay, keep that in mind. So what I notice is I'm dealing with a negative x squared, but that's easily solved. All I have to do is take out minus 1 as a common factor from all of these things. So if I take out minus 1, that gives me minus 7 plus 6x plus x squared, because when you take out minus 1 and everything, it just changes all the signs. Okay, so I now end up getting y equals minus x squared plus 6x minus 7. So now I've got my quadratic equation ready for the completed square form. So y equals minus. Now let's leave the spaces as we do. Keep the x terms together. Leave a space. Put in the minus 7. Leave a space. What are we going to do here? Take the coefficient of x, half it. So it's half of 6 to be squared. And a half of 6 is 3 squared is plus 9. And again, you've got to neutralize the plus 9 in the second box with a minus 9. Okay. And then we begin to tidy it up into the form that we require. So minus, this quadratic now has 2 identical factors. It has to have, because we've made sure by doing this at the manipulation that it will have. Okay. So first of all, x squared is x by x. Factors of 9 that add to 6 are plus 3 and plus 3. And lastly, minus 7 minus 9 is minus 16. So now I have my completed square form. But here's the key thing. First of all, the leading coefficient is negative. So this is going to be an N-shaped graph. Okay. When I take out the x plus 3, set it equal to 0 and solve it, I get x equals minus 3. See that? So therefore, x equals minus 3 is going to be the axis of symmetry. But not only that, x equals minus 3 and y equals minus 16. So when you put those two together, you get the vertex, which works out as minus 3 minus 16. So there's your axis of symmetry. The axis of symmetry is nothing more than the solution of x that's in that bracket. Okay, you take it out, set it equal to 0 and solve it. And then the vertex is the solution to that little term that's in there with the final constant, in this case here, minus 16. Okay. Let me just check. I suppose I could go back. Let me just go back here, do something in terms of the brackets. Let me just take that out there for a moment. Okay, let me just go back here. And I'm going to let the minus in. So I'm going to put the minus in. Minus x plus, I should have done that first actually, x plus 3 to be squared, and I forgot to do that. Minus by minus is plus 16. That's my mistake. So we still get the same axis of symmetry, but now what have we got? We've got x equals minus 3 and y equals, that's better, 16. So I forgot to you have to let the minus back in. So once you get the completed square form inside the brackets, you've got to drop the major brackets on the outside, allow the minus in. So that becomes minus x plus 3 to be squared, and then minus by minus is plus 16. So you get minus 3, 16 as your vertex, and you get the axis of symmetry of x equals minus 3. Okay, so just to run through this here. Notice it says that minus x squared does not have two identical factors, so we rearrange it, and we've taken out, as we said already, the minus, and we end up getting, as we said earlier on, the turning point of minus 316 and the axis of symmetry as minus 3. So it's the same thing, okay? Now, here's what I'm going to ask you to do. I'm going to stop here. I'm going to ask you to pause. I'm going to ask you to go to parts 1 and part 2 only. So in questions 12, 13, 14 and 15, I want you just to do parts 1 and 2. Okay, now that might be, I haven't got the book with me here. It might be parts 1 and 2 only of questions 12 and 13. I'm not too sure where it's 14 and 15 as well, but you can look it up yourselves. But just parts 1 and 2. It goes on talking about a whole heap of stuff underneath that, which I'll do in the next class. All I want you to do in questions 12, 13, 14 and 15, parts 1 and 2, which involve getting the vertex and getting the axis of symmetry. Okay, and we will have a live class on Friday, and in that class then we'll go back over the questions in terms of linear functions, quadratic functions, transformations, and this thing here, which is the completed square form.